If a billiard ball and a styrofoam ball of approximately the same diameter are simultaneously dropped from a modest height, the two do not fall at the same rate. The heavier billiard ball attains a greater velocity and arrives at the ground first. With the more massive ball falling at a greater rate, one might be drawn to the conclusion that an object's mass determines the rate at which it falls. However, this is not the case. All objects falling through a vacuum will accelerate at the same rate of 9.8 meters per second squared, regardless of their size or mass. This acceleration can be observed by using stroboscopic lighting flashing at constant time intervals. The distance between successive positions always increases, verifying the presence of a uniform acceleration acting throughout the entire fall. An entirely different result is obtained when a relatively light sphere is dropped through the air. Note that the sphere initially accelerates as seen by the increasing distance intervals at the start of the fall. However, during the final part of the motion, the distance intervals no longer continue to increase, but approach a constant spacing, indicating a constant velocity. This behavior can be attributed to collisions with air molecules that exert an upward frictional force during the fall. This frictional force is called air resistance and is velocity dependent, becoming greater as the velocity increases. Air resistance also depends on the density and temperature of the surrounding air, as well as the object's surface area. The speed of any object falling through the air does not increase indefinitely, but eventually reaches a constant maximum speed called the terminal velocity. Ultimately, the speed attains a value for which the downward weight force and the upward air frictional force are equal in magnitude. At this point, the net force which is acting on the falling object is equal to zero, and according to Newton's first law, it will cease to accelerate and continue its motion at a constant velocity. In other words, it will have attained its terminal velocity. Viewing the original experiment with the aid of stroboscopic photography shows that the less massive styrofoam ball on the left does in fact attain terminal velocity, as shown by the constant distance intervals toward the end of the fall. The more massive billiard ball on the right continues to accelerate and does not attain terminal velocity. However, being given a greater distance to fall through, it too would eventually reach a point where the air frictional force equaled the ball's weight, and terminal velocity would occur. For the two falling objects, both being of the same surface area, mass plays no role in affecting the rate of gravitational acceleration, but only determines how quickly terminal velocity will be attained.